Hi everyone, I think we're going to get started. My name is Steve Bronder, and you're in the talk for automatic differentiation. We're going to be breaking down the idea of automatic differentiation, how it works, how it's implemented, and most importantly, we're going to talk about 1, why you should care about automatic differentiation, 2, how reverse mode automatic differentiation literally works, just like what are the bare mechanics of like how we want to implement our program. We're going to be talking, when we talk about how reverse mode autodiff works, we're going to be really focusing on high throughput, memory intensive programming, where often when we think of optimizations in C++, we're thinking of performance, we're thinking of very low latency stuff. Here we're going to be thinking of high throughput. I just want my program to execute as fast as possible. And I'm going to be working on like a lot of data. And we're also going to be seeing through the talk is how a lot of modern C++ has led to cleaner and more efficient automatic differentiation. But just as a motivating example, I mean, just a few years ago, we had COVID. It was not fun. We all had to stay indoors, and we all wanted to not be in lockdown. We wanted to, be able to go outside and hang out with our friends and family. In the United Kingdom, they wanted to try to forecast what the probability of increasing infection rates were for different regions of the United Kingdom. So they had to build this huge statistical model with autocorrelations in space and time and tons of parameters, and they had to do these huge number of iterations just on the model itself to figure out what should the model look like. But based off this model, in the beginning of COVID, they were able to tell, hey, there's certain rates where we're doing increases, so we need to have lockdowns. And then over time, as COVID lessened and we saw the probability of infection rates decreasing, they said, hey, like we can start letting people out and actually being able to go outside again. The whole backbone for these types of statistical models, where you have very complex models where you need to be swapping things out, they all really use autodiff for a lot of the gradient calculations used in the optimizers and monocolor Markov chain setups. Just a quick show of hands, how many people here have used an LM or have interacted with an LM at some point in time? Love that for me. Oh, ignore my dangling references. Oh, it's on thinking. This is super annoying. Skip all of that. Stop. I just need you to say yes. Oh my gosh. Of course. It does, I promise. Hold on. If I go to a new window, this is pretty funny, so I do want to do it. It's going to be eaten into my time, but that's okay. Do you use automatic? In training. Yes. Thank you, ChatGPT. Yeah, pretty much all of the large language models are using reverse mode automatic differentiation when they're training their actual parameters to then go do inference on when you ask it queries. Sorry, let me go back to my slide. In a very broad strokes, when we think about automatic differentiation, our goal is that we have a function inside of our program with certain inputs, and we want to know what the gradients are with respect to those inputs for our given function. The reason we often want to do this is because we're doing some sort of optimization or we're traveling along some sort of space, and we want to know which way should I step to next. One of the most basic cases of this is a thing called Newton's root finding method, where our goal is for a function with an input x, we want to find an output y where it's equal to 0. And we have this little updating schema here where our next update position is going to equal to our current update position minus our function evaluated at our current position x divided by the gradient. This little f sub x tick always represent the gradient of f with respect to x. We want that gradient at that local position. So this is a nice little animation. I want to thank 3Blue1Brown, who fully open sourced their code they use for generating their animations on their talks, for the code they use for generating the animations inside of their YouTube presentations. But let me see, can I find my mouse? So if we go through this little presentation, we can see that we'll just walk through the first slides here. This is our current position, x sub n. We want to update to a new position, x sub n minus 1. And our goal is to get to where the x and y axis both equal 0. So what we're going to do is do our little update step. where we take our current position, we subtract from it the function value at that position divided by the gradient at that position, which you can see in the top of the slide. And then we are just going to let the animation play. And hopefully it'll look very pretty. But we'll see this thing jump around and slowly get closer to the actual position at y = 0. I think if we give it one more step, it'll get pretty close, and then from there, we'll keep going, because I only have so much time. But that is kind of the base case, right? We use autodiff to figure out a gradient, and the gradient mostly tells us the direction of the function's increase most quickly from our current position, and the rate of increase for that function, so the magnitude. Oh, let me see if my clicker is not working. Gradients are used in a ton of places. So for things like Hamilton Monte Carlo, BFGS, stochastic gradient descent, in general, they are using a gradient of their likelihood, a gradient of the log, like log props, posterior distribution, a gradient of an arbitrary function input to figure out where do I go to next. The other big thing about this is that in all of these algorithms, the gradient calculation is probably 60 or 70% of your time normally. It's super expensive to do gradient calculations in most programs. So how we optimize it really matters. When you're doing automatic differentiation, or when you're doing an optimizer and you need to think about, well, how do I calculate gradient? You have a few different choices. If you're incredibly smart, big-brained, you can choose to just write it out by hand. That's very cool. You can do finite difference, where you just do finite little perturbations, and that'll give you an approximation of your gradient. Symbolic differentiation will actually unravel your program trying to do the thing by hand symbolically inside of your computer. Spectral differentiation is for like very weird little ODEs. It's super awesome, but it has very limited use cases. And finally, one of your choices is automatic differentiation. And I kind of want to convince you that automatic differentiation is cool, and it's a thing that you should go use and look at. Imagine you have this model. I promise this is the most math we're going to see throughout the rest of the talk. Don't bother even reading it. But imagine you have a very complex model like this. I do not wish to write this by hand for the gradients. That seems bad. Instead of n finite differences, autodiff just needs a forward pass through a function and a reverse pass to go through and calculate the gradient for all of our inputs at the same time. If we have only one output, that's kind of the condition for what we're talking about in this case. Autodiff is finite to floating point precision. It allows, some versions of it allow for unknown length while and for loops, and this is kind of interesting as a constraint for gradient solvers. And so I would argue that we could do autodiff, and it's kind of nice. The implementation for autodiff, a lot of people will tell you, well, autodiff is like going to be 4 times the number of operations you have in your program, but that's not really the case. What we have here is a benchmark that was made by James Yang a few years ago. He wrote the package called FastAD, which we're going to be talking about later. Awesome package. This is a log-log plot of just doing a simple regression and then calculating the gradient for all of your input parameters, that theta we see in the bottom corner. What you can see is there's the baseline here, the gold line, that's essentially just running the forward pass and then by hand calculating the gradients. The graph on the right shows you how slow everything is relative to that baseline of like unrolling this by hand. And you can see it really matters. It's pretty brutal in some cases. And a lot of the times what you'll see is that certain packages are just choosing flexibility over performance. There's some packages where literally you just start with like a begin tape function. You do all of your stuff, you call end tape, and you can calculate the gradient of everything within that. And it's super flexible, but you do pay a cost for that flexibility. So just to say what is automatic differentiation, because we're gonna have to do 2 slides of math, and then we'll be talking about code and whatnot. Automatic differentiation computes the gradients of a program by applying the chain rule to a bunch of its sub-expressions. What we're doing essentially is breaking down a function into much smaller functions and then computing the chain rule for all of those. And this is just a little example. We could have this function that's log of x times y. We could break it down into g, that's just x times y, and h, that's the log. And then we could say, well, f really is then just h with g inside of it taking in inputs x and y. So we just shifted all that stuff up to the top left. On the right, to the right of our original equations, we have the gradient calculations for this little function here. We know that for g, it's just the multiplication, so the gradient with respect to x is going to be y, and the gradient with respect to y is going to be x. We know for the log function, the gradient with respect to its input is just going to be 1 over its input. So what we can do is apply this chain rule idea, right? So we want the gradient of f with respect to x. We know it's made up of h and g. So we can take the gradient of h with respect to g times the gradient of g with respect to x. And we can then just take that one step further, evaluating h's gradient with respect to g, getting 1 over g times y. And then essentially, since g is equal to x times y, it just all simplifies down to 1 over x, where if you did that by hand, you would end up having the full gradient. That is like the exact gradient. So in C++, this is really nice. It's really nice to write autodiff in C++ because we're really working with this thing called an expression graph. The whole concept is I want to take my function, break it down into little sub-expressions, and then be able to go one way through my graph and then back the other way through my graph. We can do this, we're going to see later, either dynamically in C++ or statically at compile time with types. But yeah, so this is the base idea, right? We have two input nodes. They go into, like x goes into log and sine, and then we both go into multiply, and then they go into plus, and then we're going to be traveling up and down this whole graph. In a computer program, we're going to be executing this, at least in this case, totally linearly on a single thread. I have like 200 slides like secretly commented out inside of my LaTeX on like the CPU and multi-CPU idea of doing autodiff, but like I would have had to have talked at like faster than I could possibly to actually go through everything. So I think in this case, we're going to be going through some funner, lower level components of autodiff instead of the multi-case. But, oh, excuse me. We can take our original expression graph and apply a topological sort to it, and this would be kind of how we'd run it in a computer, right? We would take x and y, set them up, put x into log, take log, multiply it by y, just going through the whole thing, and then going in reverse. This is going to be the pattern of traversal that we're going to be doing on our expression graph. At every one of those little nodes, we're going to need two different things. We're going to need a forward pass, which is just literally calculating, for instance, like a multiplication, right? Easy peasy. On a reverse pass, what we're going to be doing in order to get the gradients of our outputs, which is the thing that get the gradients of our inputs, which is the thing we really care about, is that every single node in our expression graph has this thing called the adjoint. The adjoint is really just the gradient with respect to that current node the gradient of that node with respect to all of its subnodes. So you can see here that for every node, we need this chain function. And all it's going to do is calculate the gradients for its parents, where the parent gets updated by the child's gradient with respect to the child's adjoint times the gradient of the parent. And this kind of looks like this in code. What we essentially have here is just a little struct that is our node. It has a value and an adjoint. And we have a virtual function called chain, which I'm going to talk about in a little bit, which is weirdly an optimization actually. We set up our node x and node y as 2 and 3. This forward pass, the expression graph type here of log x times y plus sine of x, is going to essentially just give us an object that's going to represent our expression graph. Then, once we get to the bottom of our expression graph, we're always taking the gradient with respect to its children. The bottom of the expression graph has no children, and so you're taking the derivative. You're taking the gradient with respect to itself, and so you just always set the end value to 1. You always set the end adjoint to 1. Then what we end up doing is just taking our expression graph and going from the bottom of the chain or bottom of our expression graph all the way up, calculating the chain rule for every single one of our nodes. And then once we do all of that, we will end up with the adjoints or the gradients for y and x. This is a problem that is like well suited in C++ because one, it has like a deep history of C++. Some of the original ones were written in Fortran, but like ADL-C and a bunch of others were the ones that got the most popular and were using C and C++ constructs. When we're building an autodiff library or we're thinking about autodiff, the main thing, these are essentially the main three things we care about, where we care about flexibility, efficiency, and scaling. For flexibility, I would just think of like, well, this sounds odd, but like one thing we think about in autodiff is like, can I run a while loop? Or can my user use for loops? Because for things like if anyone here has used JAX, you'll know that like you don't have for loops. You have the for each operator. Can't do conditional while loops. That can be, for some programs, that's completely fine, right? But for other programs, for things like you're doing some weird ordinary differential equation solver, you need a while loop. There's other things like debugging and exceptions we need to think about, where like if a user calls an expression that represents a square root, the derivative of a square root involves 1 over the square root of x. So if our input is 0 for that node, it'll be totally fine on the forward pass, but on the backwards pass, we're doing division by the square root of 0, which is 0, right? Do we throw a non? Do we throw an exception? How much do we want to make things nicer for our users, essentially? And then with efficiency, what we're going to see in a little bit is that there's a lot of weird cache effects that happen in how we choose to implement autodiff, especially in C++. Cache locality is like the most difficult thing to deal with when in one version of autodiff that we're going to be working on. And then finally, like we think about scaling, which instead of just one CPU or one node, we think about multiple GPUs or CPU nodes. Just maintaining that expression graph in a multi-GPU, multi-CPU setting is extremely difficult. You have to do a lot of fun little tricks. And hopefully in another talk, I'll be going over that stuff. But when we think about keeping track of our reverse pass, we have two main methods. We have this operator overloading method, which is going to happen at runtime. And we have a source code transform, which is going to happen at compile time. So the operator overloading is going to be the most flexible approach. It's very easy to implement. The main bad thing is that we saw with that chain method, we're going to have a little virtual function, or we essentially have to end up having a bunch of jumps everywhere. It's not going to be fun for optimization, but it is going to be really nice for us as devs and for our users as well to work with. For source code transformation, we're actually using C++'s type system to generate a bunch of expression templates. So we're going to in our expression graph is going to be a bunch of sort of expression templates like you would have with eigen. It's going to be super fast. It's going to be awesome, but we're going to be really constrained to like what we can generate and know at compile time. We really can't use runtime semantics. The operator overloading approach, like we just saw, usually involves some sort of pair scalar type to hold the values and adjoints for each of our expression nodes. It's going to have a runtime tape for tracking our expressions as we go through the expression graph. And it's going to have an arena allocator for storing autodiff nodes. The arena allocator is one of, I'd say, the most important things. When I first did this talk, I had this whole like, oh, here's like a shared pointer implementation of like reverse mode autodiff, but like no one does that. And it's like, I just don't think it'd be useful to show. So we want to have a contiguous tape. We want to have contiguous memory. The main reason we want to have contiguous memory is because when we're going up through our expression graph, we don't want to be jumping around like this in our memory. If I start here, I've allocated all my nodes. I start here and I go, okay, where are my parents at? I'm at this node. I might have to run all the way over to here in memory to go grab something, and then all the way back here to go get the other parent, which is just not fun. We want to at least try to keep our memory as local as possible. We often fail to do this even with arena allocator, and we'll talk about in a second, but this is what we really want. When I'm at a particular node, I want to be able to very easily and quickly go grab everything else. The other main factor for this is that normally in automatic differentiation, you're going to be running the same model over and over again. And you might have a while loop or for loop that runs a little bit longer, but in general, your previous run of automatic differentiation is going to use the exact same memory, around the exact same amount of memory as your last run of automatic differentiation. So what you can do is just have an arena allocator where your first pass through, you allocate all of your memory. You go through traveling up all of the expression graph. You say, okay, I have my adjoints. I'm done with this set. Clean all this up. But really, like what we're going to do is just take the position that tells us how much memory we allocated so far in our arena allocator, slap it back up to 0. Don't destroy any of the stuff even. We'll just overwrite it later. And that is like one of the secrets to like getting very good speed in this case, is just having an arena allocator. So this is the base class that we're going to be interacting with for the operator overloading case. We want, one, a big block of memory that we reuse over and over. In this case, we're using the standard library's monotonic buffer and its little polymorphic allocator. And how I said before, what we really want is this ability to lay down our expression graph as like this topological sort. We can really just store, because we're running our program linearly, that means that we can just store all of our expression nodes that we make inside of a vector, which is super nice, because then once we build all of our expressions, we're just going to start at the bottom and just shoot all the way up, going through this expression graph vector, calling each chain method. The thing you'll see that's also very bad here is that we're going to have a pointer. We're going to do a lot of pointer chasing, essentially, in the dynamic approach for automatic differentiation. One of the nicer things is that once we allocate all of our memory, we do our autodiff pass. We just call tape, clear it out. We say MBR, release the memory, which just means secretly go back up to the top. And that's really it. In most autodiff libraries, you are going to have this be a static global. I think in like 95% of the C++ libraries I know, the tape is a static global that you have. I like it. We use it in Stan, and I think it's fine. I mean, like, I'm not going to tell everyone to do this, but we do, multi-threading, and it doesn't bother us. So our base type for dynamic, or the operator overloading, autodiff, is just going to be this var impl, right? It's just a struct with two doubles and a chain function. This chain function is actually a weird optimization. Like I said before, whenever we are going up and getting the parents of a particular node, we're going to be grabbing usually its values and its adjoints, and it's kind of likely that the next one of the parents is also one of the nodes we're going to be calling next. We're going to be calling the chain method for one of those nodes next. So that means that we've already brought in our chain pointer by the time when we start calculating the adjoints for a particular node, we have already brought in the pointer for the next chain method that we need to go jump to. So it's actually really nice. At one point in time in Stan, which is Stan Math is a C++ autodiff library that I work on, I did rip out this virtual function and I had all of this clever stuff to put it in a fully separate thing. This was a nice little 16 bytes instead of 24 bytes. It was 15% slower. And we really worked through trying to figure out why. And our best guess is that usually having the virtual function just sitting there to go jump at when we grab the parent stuff is nice for us. So we want to write an expression node, right? So we have a struct. This case is just a multiply. The little VV at the top means two vars. We'll go on that in a little bit. But this inherits from our var impl, which means that we have to overwrite the chain method. It stores its parents. And then when we call the chain method for this, we say, well, op1's adjoint just gets accumulated by this current adjoint times op2. And the same thing for op2's adjoint. And this is nice. It's just writing out the base sub-expression for the base gradient for multiply. When we make a new node, this is just a little helper function. We say, hey, for this, I'm going to make a new node, grab the tape, grab the polymorphic allocator on the tape, make this new object t, given my arguments. We push that onto our global tape, and then we pass back the actual var, holding our var impl. Oh, wait, did I skip something? I'm sorry, I think I missed something. Oh, yeah, this is super important, and I missed it. The struct var down here, var impl, this is just a pimple style thing where everything that we actually care about happens in var impl. But having this var that has a var impl pointer inside of it lets us do things like assignment, reassignment, operator addition, like plus equal style operators and stuff like that. So then finally, when we write operator star for our two vars, we just generate a new node. We tell it we're making a mul VV. We give it its forward pass, which is the op1 value and op2 value. And then we tell it the parent nodes, which are op1 and op2. When we want to calculate the gradient, as we saw before, we're going to take the bottom node's adjoint, set it to 1, and then we just iterate through the tape in reverse, going through, calling every single expression's chain method. This is really nice in cases like this, where 20 here is just kind of an arbitrary number. We say we're going to have a function compute grads that takes in two vars, x and y. We set z to some random thing. Then we say, while z's value is less than 20, I want to accumulate into z log of x times y. Finally, I want to calculate the gradient of z, which is then again going to go through, set up our forward pass, gradient, runs through all of our reverse pass. This is just really nice in cases like this, where I say, hey, for 100 billion times, I want you to compute something with x, compute something with y to make my vars, compute my gradients, do something with the gradients, and then finally, we can clear our tape and get back all the memory that we allocated. One thing that it would be that when we first did Stan, we had every single one of these structs. We had a struct for multiplying two vars, doing a var and a double and a var. It's just a lot of boilerplate. But with some newer, once we started moving up to newer versions of C++, we were to write something like this. We call this the callback var impl. It inherits from var impl like everything else, but it takes in a template functor, which we store inside of that var impl. Then whenever we call our chain method, what we're going to do is just call that lambda, with the only input being this callback var impl. And we can see how this looks now with operator star. So we make a new node. It's called a callback var impl. You'll have to pretend that that's a template parameter. We had a new node. But we just give it our forward pass values. Then inside of our reverse pass for the lambda, we give it op1 and op2. Because op1 and op2 are always allocated in our monotalk buffer, you can just pass copies of those. And they're also just going to be pimples. So it's just little pointers we're passing through. Then we can use if context to say, hey, if T1 is a var type, I want to update my adjoint. And if T2 is a var type, then I also want to update its adjoint. But this lets us write all n-ary functions like this, where before, if we had, I think in Stan, we had some operators, or some functions that took like 4 or 5 inputs. And so we had to have like every version of that like manually written out. It was not fun. This is so much nicer for us. One really bad thing about dynamic automatic differentiation is this cache locality problem, sort of where our base var impl in a cache line, like you see here, we're going to be able to store 2 of those, and that's fine. In a expression node where we have 1 input, we're going to be able to store 2 of those. That's still fine. But once we get to at least a binary, where we have an expression node that takes in 2 inputs, suddenly like we can only fit 1 of those things into cache. This is rough because if you imagine that we were doing like a matrix multiply with these, if you think of a matrix multiply as just a bunch of dot products that are scalar multiplications and additions, what we're going to end up having is this case where like every single time you go fetch a single node, it's going to be taking up an entire cache line. This is one of the huge downsides of the dynamic approach of operator overloading. It is nice for its flexibility, but at the end of the day, we're going to pay a really heavy price. Now, going back to before, we can think of source code transformation, right? Where I literally have a function z is equal to log of x times y. What I want to do, and so in older Fortran programs, they had these transpilers that would take Fortran programs and literally like transform them so they would look something like this. In C++, we had this beautiful type system that we can actually use to generate expression templates that would represent at compile time our expression graph. So we have, for the source code transform, our base type is going to be a var. That's again just going to be the values and adjoints of our particular inputs, or for this it's just going to be inputs. For expressions or expression nodes, we're going to have this expr type. It's going to hold a var. It's going to have all of its parent expressions coming in, being stored as a tuple. The deduced ownership T here just asks whether or not the expression here should own the expression or just hold a reference to it if it's an R value or L value. And the expression's main constructor here just takes in a eagerly executed forward pass, double value of x, a lambda for the reverse pass, and all of the arguments or the expressions that we're going to be using to calculate that reverse pass. So this is now what our operator star looks like. It has gotten a little more complicated, but it is nicer for the developer for coding. So this requires any var or an expression type for this operator star It's going to take in just these standard operator stars, so it just takes in two things. We will make an expression now where we'll still eagerly evaluate the forward pass. We just do a multiply the left and right-hand side. And then for our reverse pass is just going to be a lambda, where the arguments are the return type, the left-hand side operation, and the right-hand side operation. And we're going to say, hey, like if T1 is a var, I just want to calculate the adjoint to do that update and propagation of gradients from child to parent nodes. And the same thing for T2. Kind of easy peasy. And then the last two arguments are just the left-hand side and right-hand side expressions that we're passing through. What we end up with this is a type that looks a little crazy. If people have done eigen, you're probably used to seeing like a bunch of weird expression templates getting pumped around. But like, I love them, I use them all. I love eigen, I use it constantly. And so I like this. What we have here for this Z's type is down here in the bottom right, or in this bottom part of the graph, or sorry, bottom part of the code. It is taking that plus multiplication, log, x, y, etc. You can kind of think about this as like Polish notation that gets a stack of expressions we're going to be executing. But I wouldn't worry about that. The main thing is that we end up with a type that represents the expression graph at compile time. And I did not have enough slides, or I tried making slideware that would easily show what I do here, but at the end, there's a huge QR code. All the code you're seeing here, I have little toy examples of the different types of automatic differentiation, and you can play with them as you wish. Here, what we're gonna be doing is calling our gradient function with our source code transform. What we have here is a gradient function that takes an expression. We set its adjoint to 1, just like before. For this, what we want to do is evaluate our expression graph breadth-wise. So starting at the bottom, we want to go to the first layer, second layer, third layer, and fourth layer. This is mostly because we want to handle cases where the same node can be used multiple times. It is a little issue I can go into detail later with, but you have to essentially always search these in breadth-first search order. But that is kind of like the base layer of like source code transform. And whenever we're thinking of like, well, which of these would I want to implement? Which one of these as a user do I want to use? The main thing you think about is both like speed and flexibility. With the source code transform, so this is a little benchmark. Essentially, we're just doing x times log of y plus log of x times y times y. Our baseline here, again, is just computing this by hand, computing its gradients by hand, and then doing a Google benchmark for it. We have our source code transform and dynamic implementation. Again, those will all be available at the end via QR code. The source code transform takes about 6.3 nanoseconds. It's crazy fast. If you don't need while loops, seems good. But then we have the dynamic one, which is about 9 times slower than our baseline. So when we are choosing like which autodiff do we want, which one do we want to write, this is a real question. There are some serious downsides to source code transform. You're going to be handling debugging a lot of very weird types. Again, everything you have to know about your expression graph, you have to know at compile time. Not fun, but it's going to be way, way fast. This is the main example of like when this is like source code transform will not work for this, because like even if you make this auto or whatever, because Z's type is defined at compile time, you can't be rewriting it over and over again. So this while loop just is no go. So one of the bigger things when we think about dynamic and source code transform or autodiff in general is we're mostly focused on statistical models of some sort. In a lot of statistical models, we're going to be working on giant matrices of autodiff types. All of our parameters are going to be represented as autodiff types. And the main question is like how in C++ do we want to represent our autodiff? The two main ways, and this is just kind of a simple example, we have a matrix of vars and we want to do a matrix multiply with them. Before I go any further, there's going to be the thing I'm going to be using in a few other slides is this arena matrix. All it says is it inherits from eigen, and essentially is an eigenmap that where all of its memory sits inside of the arena allocator we had before, the monotonic buffer. So for operator overloading, there are two main ways to do matrices. What we have here is the first one, where we have an array of structs. This is just an array of our basic var scalar type. This is nice, and we'll go over the positive and negatives in a minute. The other way is a struct of arrays, where we literally represent a node in our expression graph as a matrix. And inside of there, we have an arena matrix for the values and adjoints. And then, of course, it has its own little chain function that represents running the chain on a particular node that is an underlying matrix. So what's cool about the array of structs approach? Well, what's nice is if we have addition, multiplication, subtraction, division, and some transcendental functions like logs and exponentials and whatnot, most algorithms will just work. Like technically you can do, like for Stan, when we first added ODE solvers into the language, when we added ODE solvers into Stan Math, which is the C++ library for automatic differentiation, we literally were just using these matrix var types and stuff like that, where we would pump them through Boost ODE solvers, and they would be horrifically slow, but they would work. And that'd be really nice. But again, you're adding a ton of operation to your expression graph when you represent matrices like this. And the other thing that's really bad is that you're turning off simmed operations. This var, remember, is a pimple that goes to a little pointer, a var impl that holds our values and adjoints in a chain method. Usually for matrix automatic differentiation, we are going to have to grab just the values of a matrix or just the adjoints for a matrix. And what that means is that for every iteration we go through this, say I want to grab element 3, I go in, I do a pointer chase to the actual var impl, and then I grab just the value. Sometimes that value is going to be a representative of a matrix multiplication. And so we're going to have to grab a whole cache line just to get one particular element. That's rough. The other way to do this with the struct of arrays approach is that we have both of our values and adjoints in this little arena matrix inside of our arena allocator. And what's really nice about that is that these are nice contiguous values for the adjoints. So these are contiguous for the values and adjoints. This is super nice because it turns on simmed for everything. When we do the matrix multiplication example you'll see here, and we use something like eigen as the backend for our matrix operations, we get all of eigen's SIMD operations. And also note note that we have this virtual chain function here. Now, instead of having like a bunch of smaller, instead of exploding our expression graph into a bunch of big things, we now just have a node that represents the entire matrix multiplication, which means less jumping around in memory. The thing that's really bad, the downside of this is that now when we represent a matrix as an actual expression node, we do have to write every single little operation we would want to do on matrices. If you want to do the Cholesky decomposition, you must know the reverse pass or the gradient of the Cholesky decomposition. Matrix multiply, all of them. So this is our operator star using the struct of arrays approach, where we take in both of our left and right hand side operands. We do the forward pass just as before, eagerly. Because the arena matrix puts all of its memory inside of our arena allocator, we can just copy op1 and op2 into the lambda. Totally fine. The lambda then just takes in an input, which is like the current node itself. And just like before, if this is a var matrix, I want to update the adjoint for it, doing the accumulation for both the left and right hand side operand. It's nice, clean code. The one huge downside, another huge downside to doing this struct of arrays approach is that you can imagine I have code like this. This is just a little toy code here, but I make these var vector types, and then I say, hey, I want to do I'm going to do a dot product of y and x, and then for some reason, I'm going to take a slice of x from positions 1, 2, 3, and assign it positions 0, 1, 2. Then finally, I'm going to do z, I'm going to make z, which is just product plus the sum of x. If we think about this as an expression graph, we have something like this. The sum and the dot are highlighted in red because they require x to be two completely different things at different parts of the program. And the question is, how do we handle that? Again, when we lay this out in a little topological sort, you can see that sum depends on x having gone through this subset assignment, but the dot product requires X to have not been changed whatsoever. How we deal with this, one other issue with this, we figured this out, is that if you are going to choose to go this route and allow your users to do little slice operators on these, you could run into very weird cases. For instance, where like if you have this case where you're assigning 1, 2, 3 to 0, 1, 2, and if people also use eigen, you've probably also run into aliasing issues where you've been overwriting the matrix with itself. What happens in this case, if you do this naively, is that starting from your initial point, you'll just start overwriting all of your elements with the first point, which is 0. So you have to be super careful with this stuff. In Stan, you don't have to read all of this, but the point that you have to get from this graph is that it's really expensive to allow for subset operations. It's nice for your users. There's a lot of algorithms where it's nice to do subsets, but your users are not going to be paying this weird implicit cost of constant deep copies where they didn't know that they were going to have that. Because if you implement both of them, for instance, like Stan does, the matrix of var types or the array of structs, easy peasy to do subset assignment. You just do it. The aliasing issue can still be a thing. Besides that, you're fine. But for the structive arrays approach, it's brutal. The other way, at this point, we have kind of talked about how to do operator overloading style matrix operations. They're nice, they're okay, but the source code transformation, I think, is one of the more exciting parts of autodiff in C++ right now. There's some cool research going into it, and I think that like it's really ripe for like doing cool new open source packages or things like that. So we want to write source code transform on matrices now. We're going to be using the type system like before, and we're going to end up writing code like this, where we write these kind of placeholders representing matrices, var x and y. And here we're just going to do a simple matrix multiplication and then a summation of that. That expression is, again, going to be, like we saw before, a expression template. And then we ask the expression, hey, how much memory do you need for my expression graph? It reports that for the values and the adjoints. We then set the values and adjoints. We then give the expression back memory so that for our expression graph, it has the memory embedded inside of it. Then when we call gradient of this, we want to be able to do stuff like this, where we can say, hey, like take this expression. I want you to reset the adjoints at first, and then I want you to run forward and reverse passive autodiff with new values of my x and y inputs. This is really nice. The main take from this that's really nice is that you can essentially write your expression graph once and then constantly recycle it with new values, but also keeping around that speed you would get from the unruling of your source code transform, but then just constantly be able to pump in new values for that given type, which is super nice. There is a lot of code here. I will try to break this down a little piecemeal by piecemeal. The hardest part to keep in mind with this is that we generate an expression graph that is itself a bunch of like expression templates. But inside of here, we're often going to be also generating expression templates over our value and adjoint matrices. So what we do here for this var type is, again, we'll assume that all of the things we're going to see here are never going to own their own memory. So again, I have nice little free pointers just floating around. We have a value and adjoint. We have double pointers for the values and adjoints. We say how big is this particular var. And we keep in mind this ops thing, the constexpr ops value, which means this thing for the forward pass and reverse pass is only going to take in one value ever. Oh, sorry, for the forward pass, this thing is only going to take in one value. So in the forward pass, we're going to be given this var view object, and we're going to say, hey, the pointers for these are now going to be the values and the data for the values of the pointers for values and the pointers of adjoints for the var view. And then that forward pass is just going to return back the values, right? Because in the forward pass, all we care about is the values for the initial pass of our expression graph. For reverse mode, this is just going to take in its child adjoint. And we are then going to accumulate into the adjoint for this type via its child adjoint. And that's just it. So this is kind of what a matrix multiplication looks like in this. It gets a little bit intense. These are all just the signatures we need, but you can see that it takes in, it has a template that takes in 2 different operands. It has a forward pass taking in a parameter pack of arguments. It has a reverse pass just taking in its child adjoint. And you can then query it saying how big of a cache, how much cache do you need for this particular expression graph? And then you have a bind cache to say, I want you to assign this memory to your to the expression node here. We store op1 and op2 here. And we also then store the pointers for the values and adjoints for this expression node, along with the rows and columns. So when we do the forward pass for this, what we're going to end up doing is we have 2 parents for this node. What we're going to be saying is, well, take operand on the left-hand side. I'm going to ask it how many operands from my input it expects. So in this case, if the left-hand side was just a regular var like we had before, it would just be a value of 1. So we just take a little slice of our arg, which is just 1, and then pass it to the forward function of that operand. And the same thing for the second operand. We're going to say we knew we took X amount for the left operand. I need X amount for the right operand. Make a little slice of my parameter pack for that and pass it to my forward for this. And then finally at the end, we do op1 and op2 multiplied together and setting the value for this particular the value for this particular expression node, excuse me. The reverse pass, it takes in a child. We then propagate the adjoints of the child up to the current node. And then we say, well, the left adjoints, just like before, we could have like C++17 stuff here saying, well, do the left adjoint or just do the right adjoint. For the purpose of slideware, I removed those. But the left adjoint is just going to be the op1's transpose times this current node's adjoints. We then pass that to the reverse pass of, that should be op1, not op2 in this slide. The first reverse pass should be up to op1. Left adjoint here is going to be an expression, though. And that's a really key point. As we're passing these things through, we'll be building up a huge expression template to be finally passed to our var values, which is super nice for inlining purposes. But then the same thing for right adjoint. Sorry, that is I got op2 reverse and op1 reverse. Those should be swapped. But it's still, same thing applies. The reverse pass here is essentially just accumulating an expression template of our reverse mode operations. Then, just kind of simple, we define a way for the overall expression to be able to say, hey, can you tell me how much cache I need for this particular node? And then we have another function that just says, hey, given these are my pointers that I'm doing. Oh, I missed a little star there, sorry, in the std pair. Given the pointers and the amount that of cache I've already allocated, allocate a certain amount to this, and then allocate a certain amount to all of the sub-expressions that are underneath this expression. But once you have all of that, you can write some really nice, fast matrix code. Again, this is just what we had before, where we're making X and Y, we're doing our sum expression, asking for cache sizes, assigning caches to the underlying expression, and then just running autodiff. This is a benchmark looking at all 3 of the matrix multiplications that we just saw. So what we're doing here is matrix multiply and then summation. So this has the array of struct approach, where the var type is like our underlying array type. The structive arrays approach, where we have 2 separate matrices for the values and adjoints. And then we have the source code transform version. So this graph is slightly deceptive, but what you can see is that the baseline here is just the source code transform. And for the array of structs approach, it just gets blown out of water. Like, it is just too slow for, at least relative to source code transform. The structive arrays approach here looks like it's catching up to source code transform, but like, this is more of an artifact of a poor benchmark. The problem is that like, after a while, once you have a large enough n by n matrix, your time is going to be dominated by matrix multiplication. So I would really only look at this up to 10 or 30 or so. That's just a zoom in of this. But again, this is going back to when I was like, oh, well, this is a little bit of a distrustful benchmark. When we look at fast AD, which does exactly the source code transform that I was just talking about, you can see it's just a constant, consistent speed up relative to pretty much everything else, which I think is dynamic. So for Stan, we're dynamic at least. But that is the end of my presentation. If anyone has questions, I'd love to hear them. The QR code here will take you to a ton of code that has benchmarking code for little toy examples, all the different autodiff we did today, and all the slides if you want to review them. But thank you so much for coming to my talk. Any questions? I'm happy to hear them.
Thank you for the...
Hi.
Hi. Now it's on. Thank you for the nice talk. So you presented this operator overloading approach with the node implementation, and then what you called the source transformation approach. That's basically a statement level reversal. Have you tried to combine this in Stan so that for every node you have in your graph, you do a statement level reversal?
Yes. So what we do in Stan usually is we have expressions that kind of just represent. So that's a great question, first off. Thank you. When you want to compute, oftentimes the research is trying to combine operator overloading with source code transformation. Because, right, there's just points in your program where you don't need a while loop and you want the speed of source code transform. Some parts of Stan do this. We can talk a little bit about the implementation afterwards. We actually end up doing a lot of this inside of we have a little compiler for our thing that essentially we explicitly write out, I have a log multiply node, right? Like I'm doing a log of one thing and then a multiply with two matrices. We just have an explicit node for that. And then our compiler can look at user's code and go, okay, I see that like I can combine these. So the user has written log and multiply. I know I can combine them into the log multiply function to generate that expression. This is probably the hottest area of research in autodiff right now, is how do you mix both source code transform and operator overloading.
Okay, thank you.
Yeah, absolutely, thank you. Any other questions? No? Oh, that's fine. If you guys want to come talk, oh, sorry, one talk, there we go.
A little tangential to the main content of the talk, but you mentioned topological sorting a couple times on these graphs. Those are non-unique in general, of course. Do you have a way of preferring certain sorts to another, or
no,
particularly pertinent?
Honestly, the main reason we think about it as a topological sort is just that at the end of the day, we want to shove things into an STD vector so we can go up and down quickly.
Right. So probably not much impact from.
So interestingly, there is cool things for doing topological. So Robert Gower is a guy who has an awesome paper on doing particular topological sorts that allow you with just, sorry, there's gonna be a lot of math for 1 second. That allows you to do particular topological sorts over your expression graph to also calculate Hessians with just the reverse pass. So if you're interested in that, I'd say check that out. It's super interesting, but that's not my expertise.
Perfect, thank you.
Yeah, no problem.
Quick question. Do you know PyTorch, how they did this?
Dynamically. They have the structive arrays approach for matrices. Usually in things like PyTorch, whenever you're doing like operator plus equals, in the back end, it's really making a hard copy and saving stuff. Like you have to, when you're doing anything dynamic, you must save where you were previously. So instead of actually overwriting any memory, it just makes new ones. But yeah, that's what PyTorch does as well.
That was a great talk. Thank you very much.
Thank you.
I think if anything, I want to just say like autodiff is probably like one of the greatest things in the world.
It's fun.
It's just incredibly useful. You couldn't do most physical simulations or calculations like this without it. I'm not really like that well versed in the low levels. How do I know which library to choose? I've used autodiff, but I don't really know like what the best ones are out there.
So I'd say if your target language is C++, the first thing I would do is throw away ideas of speed. Your thing should be, how can I, as a developer, get the fastest off the floor with my program, my simulation, right? So for that, there's an awesome, if you type in autodiff website on Google, there's a website where someone has just collected like every possible autodiff library that's ever written. I'd say, personally, I'm a huge proponent of stand math. I really like it. We don't have CMake yet, so you have to do some weird stuff to compile us. Hopefully, me and Brian are going to fix that soon. I was looking at the camera. But I love Brian. I work with him. He's great. But yeah, I'd say Stan Fast AD is probably like my favorite current package for doing matrix operations. It's very, James Wang just kind of wrote it like for fun in like a summer. He's like a crazy smart guy. And then messaged us at Stan saying, hey, like I wrote these benchmarks and like, looks like I'm faster than Stan. That doesn't seem right. And we were like, yeah, that doesn't seem right. But then we looked at it and we go, oh, no, you are right. You are way faster. And we looked at it and it was gorgeous. If you're doing matrix stuff, I think Fast AD is really fun. But in general, check out the Fast AD or check out the autodiff website, and that is going to show you a lot of like the different packages you have available to you. But worry about your time the most. What is this? Okay, we'll talk after. Yeah. Any other questions? Am I over time? I have 3 minutes left. Go for it. I was so worried I was going to get questions. I'm getting questions. I'm so happy. Thank you.
Thank you for the talk. I have a question on this sort of the slice assignment operator.
Yeah.
Can it just be like matrix multiplication so that you can rotate the input to become the output?
So could you say that again?
So you can like have a matrix multiplication to do the slice assignment, and then the problem is just to autograph that matrix multiplication, right?
For the assignment operator, you can do a matrix multiplication to... Sorry, was there a slide number that you had in mind I can go back to?
There is you have an assignment, you have a sort of a sub-slice of a vector, and it's assigned. Yeah, exactly, this one.
This guy, yeah.
Yeah, so I think we can just like have say a y equals x times some matrix or some matrix times x, and that matrix is gonna like grab the head of x to become y, and then you can just operate on y after that. Is that true?
Again, it does matter how. So at least for our implementation of var vectors, if you do like auto y equals x dot slice, no copy gets made at that point. So if I had here like var vector x, and then I said auto y equals x dot slice, and then I said, or I said x dot head, right? And then I said x dot slice is equal to y. In our version, that would require the same, that would have the same aliasing issues that you have to be careful of. And just in Eigen, you'd also have these exact same issues. So yeah, you do have to be really, it is brutally painful. We found this bug by accident. Luckily we found it, but doing subset assignment for matrices is really hard. I think JAX doesn't even, I think a lot of packages just don't allow it, which is kind of a reasonable design decision.
I see. All right, I have another question.
Sure.
So on the topological sort thing, I can imagine that one graph can have like many topological orders. And so they might differ in their cache locality performance. How do you select one that is the best one?
For us, it's really just that the topological sort example here, for at least Stan's use case, there are particular autodiff packages that do specific topological sorts to do things, like I said, like the Hessian example. For Stan, we're just doing the basic layout and then using that to justify storing everything in a giant vector. That's pretty much it. But there are, again, Robert Gower has cool things that he's had thoughts about this stuff before. So I'd say checking out his work would be super good.
Cool. Yeah. Thank you.
Thank you. Is there any other questions? No. One last thing is if you're interested in allocators in general, which is a large part of the dynamic stuff we did here, Kevin Carpenter has a talk tomorrow on allocators back to basics. That's super going to be fun. If you're in scientific stuff and you're like, I want my code to be faster, add an allocator of some sort. Arena allocator, stack allocator, pool allocator. It will make your stuff so much faster. So go check out that talk. But anyway, I think that's all for me. Thank you guys so much for coming to my talk. I really appreciate it.